In this problem, we're looking at the stability of the properties of the lattice properties of the uh, uh, continuity and other properties like limit for functions, real valued functions, when you take the sup and and the min or the inf. Okay, so we have two functions, and we are looking at so we have two functions, and they are defined on a domain set. And we're taking x0, which belongs to D. And to be precise, we have to take the x0 in the interior of D. So this way, we can take limits from the right and from the left. Okay? So assume that limit. So the issue is we are looking at these two functions, minimum of f of x, g of x, and the function max of f of x, g of x. So the key behind this problem is very, very important equalities I'm going to put in right now. So here, very important, okay, equalities which are very useful, extremely useful, is that the minimum of two numbers a and b, okay, is in fact equal to a plus b minus a minus b over 2, while the maximum of a and b is a plus b, okay, plus a minus b over 2. So, for example, just to give an example, let's look at the max, for example, okay? So assume that a is bigger than b. So if a is bigger than b, the absolute value of a minus b will be a minus b. A minus b plus a plus b, this will give me 2a divided by 2, that's a. And the same goes for the other one. So these relations are very important, which means, in fact, that to prove whatever you want to prove, it has to do with the absolute value, okay? So next, okay, we remark that if limit of f of x when x goes to x0 is equal to L, then limit of absolute value of f of x when x goes to x0 is equal to absolute value of a. And the reason why is because the absolute value of a minus the absolute value of b, okay, is less or equal than the absolute value of a minus. This inequality for any a and b gives us this limit, okay? So this is very, very important. Note that, by the way, the converse is not true, meaning that if you take this function for the sake of, so let's take this function, take, okay, this function here, which is 1 here and minus 1 here, okay, at 0. So if you look at this function, let's call it, for example, function h. So the absolute value of h will give me 1 all the time. So you see, the limit of absolute value of h of x when x goes to 0 is equal to 1, while limit of h of x when x goes to 0 does not exist, or if you prefer, limit from the right is 1 and limit from the left is minus 1. So you have to be very careful, okay? The converse is not true. In any case, so once you have done that, then the problem becomes piece of cake. Why? Because if we assume, okay, if we assume that limit of f of x when x goes to x0 is equal to small l, and limit of g of x when x goes to x0 is equal to capital L, then limit of absolute value of f of x minus g of x, Okay, when x goes to x0 is going to be equal to absolute value of L minus L. This is where we use, of course, the properties of the limit, and this will imply then that limit, for example, just for example, limit of f of x plus g of x minus f of x minus g of x, absolute value over 2 when x goes to x0, this will be equal to L plus capital L, L minus capital L over 2, which gives me that the minimum of f of x, g of x, in other words, limit when x goes to x0 of the minimum of f of x, g of x will be equal to the minimum of L and capital L. Okay, so what is one of the implications of this? And the same holds, of course, for the max. So what is the property here? What is the implication of this? If f of x and g of x are continuous, then the minimum of f of x, g of x is continuous, as well as the maximum of f of x and g of x. So these are very interesting properties, or lattice properties, on the functions, as well as their limits, continuity, and so on and so forth.